I would like to thank everyone for joining our workshop that will be on blockchain and interoperability and sharding. The idea of this workshop is to bring together researchers from academia and industry and discuss state-of-the-art solutions and understand also challenges that do exist in this topic. I would like to thank Eleftherios, who is going to chair this workshop with me, and I would like to thank the organizers and Moti and Yuka from DISC for their support for making this workshop happen.
For being here for our first workshop on interoperability and sharding. Our first speaker is Alexei Zamyatin, who is a PhD student at Imperial College and is also recently a co-founder of Interlay. And he's doing some great work on blockchain interoperability, and he's going to talk about trustless cross-chain communication. Is it impossible? And can we save something with incentive compatibility? Alexei, thank you very much.
Cool, thanks a lot. Let me share the screen. Great. Okay, yeah, thanks a lot. And yeah, it's great to be here. So my name is Alexei. As the Leftherios mentioned, I'm a fourth-year PhD student at the Imperial College of London, and we also pretty much a year ago founded Interlay, which is a company that focuses on interoperability research and development. And today I have the honor to kind of be the first speaker at this great conference and with a somewhat slightly controversial topic, talking about cross-chain communication in general, and also going to dive into whether it's or why it's essentially impossible, and how we can circumvent this result in practice by using incentives. So essentially the concept that makes Bitcoin work in practice. Now, this talk is based on two academic papers. On one hand, XCLAIM, which was published at IEEE SMP in 2019, and our systematization of knowledge paper, where we systematize the entire field of cross-chain communication and also derive this result that I'm going to present. So I guess everybody here with me will agree that interoperability is indeed a very important field of research, and considering the 5,000 or more cryptocurrencies we have today on different blockchains, which all differ in design and purpose, it's quite unlikely that there will be one chain to rule them all. So we will need some ways to communicate across different blockchains, ideally in a trustless and secure manner, if blockchains are to become mainstream. Now, if we look at the research behind this, we can trace cross-chain communication back to the non-blocking atomic commit problem in distributed databases. The main difference here that we can identify is that whereas in distributed databases, you will typically have, you typically assume that the information that is propagated across the systems is more or less correct, and you don't have an adversary trying to subvert the system. You can no longer make this assumption in distributed ledgers, where you have to assume Byzantine failures and Byzantine adversaries, and you typically will look at the borrower model. So with Byzantine, altruistic, and rational actors. Now, in research, we see cross-chain communication in a lot of different fields, and I'll try to give a brief overview of these. So the most typical and most common field where we encounter interoperability is cross-chain exchanges across different distributed ledgers. And we can do this with atomic swaps, where we change assets, or by using cryptocurrency-backed assets. And I think most of you are probably more familiar with the term wrap Bitcoin on Ethereum, where we move Bitcoin from the Bitcoin blockchain to Ethereum. However, these principles are also found in sharding, specifically when we want to communicate across different shards, blockchains or shards within a system. And what is quite interesting is that the first cross-chain communication mechanism to be deployed in practice in 2011 already was actually merged mining, where basically this technique was used to bootstrap Namecoin on the proof of work of Bitcoin, and Namecoin was verifying Bitcoin proof of work solutions cross-chain and then triggering state transitions and generating new blocks each time a valid or corresponding Bitcoin full or weak block was mined. And finally, another term that is very, very often used and also kind of as an umbrella terminology for this field are sidechains. And sidechains basically follow the concept that we want to extend the functionality of the existing blockchains by pegging or creating new systems pegged to a parent chain. And typically you have some parent chain relationship there where either you use the same currency or you have some security dependencies. Now, let's talk about the cross-chain communication problem itself and basically how we can model that. So typically we'll assume that we have two different distributed ledgers. In this example, we'll use Bitcoin and Ethereum, but essentially it can be anything. It can also be two shards in a sharded system. Now, we will also often assume that there are two different consensus committees. So we have Bitcoin's consensus and Ethereum's consensus. Now, we use the word committee as a generalized term here. Of course, we're aware that Bitcoin and Ethereum employ proof of work, basically to randomly elect the leader. But at any point in time, you kind of have a snapshot of a committee. So we use this kind of as an umbrella terminology here. Now, we typically will also have two participants or processes which are involved in the cross-chain communication protocol. In this example, we use Alice on Bitcoin and Bob on Ethereum. Now, we'll also assume that there are two transactions, and essentially these transactions represent state transitions on both blockchains. We have TX1, which is a Bitcoin transaction in blue, and TX2, which is an Ethereum transaction in red. Now, let's assume that Alice, for some reason, wants the Ethereum transaction TX2 to be included in Ethereum, and Bob wants the Bitcoin transaction to be included in Bitcoin. And they both know exactly how the transactions look like, so both Alice and Bob have a description where they can check whether the counterparty transaction is indeed what they expect. And while this may seem abstract at first, you can imagine that this is an exchange of assets between two participants, and this is already the first hint towards impossibility results. We can assume that transaction TX1 in blue transfers Bitcoin to Bob's to UTXO so that can be spent by Bob, and TX2 transfers ETH from Bob's account to Alice's account. And the goal of cross-chain communication is to synchronize the inclusion of these two transactions in the respective blockchains, or more general, to synchronize two state transitions on two independent blockchains. Now, we derive three properties for cross-chain communication, and those of you who are familiar with the fair exchange problem will already see the first resemblance here. We say that a cross-chain communication protocol must exhibit effectiveness, which means that if Alice and Bob are honest and they want to execute the exchange, and both transactions are indeed as expected, so they match the descriptions of each counterparty, then transaction TX1 will be included in BTC and transaction TX2 will be included in Ethereum. However, if the counterparties do not want to proceed with the exchange or malicious, and TX2 or TX1 are not as expected, then we will abort. Atomicity then restricts the potential outcome of the protocol such that neither Alice nor Bob are to disadvantage if we talk about an exchange, or that both TX1 and TX2 are included in both blockchains atomically, or none of them are included at all. And finally, timeliness is a property for liveness that we say if both Alice and Bob are honest, then at some point they will write these transactions to Bitcoin and Ethereum. So we then can derive a generic CCC protocol, and I use CCC for cross-chain communication as abbreviation because it's quite long term. And if you look at the protocols in this space, they all more or less follow the same concept. You have a setup phase where you decide which two blockchains you're connecting to, who are the participants, and also what do the two state transitions or transactions look like. So is it a transfer of assets? How much assets are we transferring? Are there any time constraints? And so on. And typically this step is handled out of band before this protocol is initiated. And so we focus on the other steps in this talk and also in the paper. Now, the cross-chain communication protocol will typically start with a commitment phase on blockchain X, and we can say blockchain X is Bitcoin, for example. And then let's say that the transaction is published in this blockchain. And then the second step is to verify that this transaction was published or committed on X, and this happens on blockchain Y or in some other manner. And then the decision is made whether to proceed with a second commitment on blockchain Y or Ethereum, or whether we want to stop the protocol and abort. And then we observe that some protocols implement an explicit abort step. Other protocols just assume that if the first state transition was correct, then the second state transition will also occur. And we do note that there are two relevant parameters here. On one hand, K, which is a persistent parameter of the involved blockchains, or what we typically also refer to as confirmations, and U, which is a liveness delay, essentially the time it takes one participant to get the transaction included in the first Bitcoin block. Now, having talked about how cross-chain communication works in general, let's think about whether it is indeed possible or not without a trusted third party. And this was essentially the goal that I kind of tried to solve during my PhD research, and we realized not so long ago that, in fact, we have an impossibility result. And the intuition behind this is that a cross-chain communication protocol can indeed represent a fair exchange of assets. And as before in our example, let's assume that transaction TX1 and TX2 transfer assets from Bob to Alice and from Alice to Bob, vice versa, accordingly. Now, we know that fair exchange is indeed impossible without a trusted third party, and there's been quite a few papers on this, one, for example, being by Pagnino and Gärtner in 1999. And what we do basically is we reduce the cross-chain communication problem as we define in our paper to the fair exchange problem. And then we derive that indeed cross-chain communication is impossible without a trusted third party. Now, without going into too much formalisms here to not bore you with this, and I do recommend, if you're interested, that you take a look at our paper, but I will try to give an intuition of why this result actually is relevant. Now, let's go back to a previous example and make our model a bit weaker, I guess, by introducing a smart contract on Ethereum. Now, let's assume that Bob's transaction is locked in the smart contract, and if Alice releases the transaction on Bitcoin, the smart contract will enforce correct behavior of Bob. Now, the protocol will then proceed with Alice broadcasting the transaction to Bitcoin, and then the smart contract will release the transaction to Ethereum, which will mean that Bob receives Alice's BTC, and Alice automatically then receives Ethereum, which will be perfect, and it seems that the protocol works. Now, the question that we encounter, however, is how does the smart contract or the consensus participants on Ethereum become aware of the transaction on Bitcoin? There needs to be some information transition, some proof data to be submitted to the participants or to the smart contract on Ethereum that enforce correct execution of the protocol. Now, this means that we have to assume one of the following two things to make this protocol always work. Either we assume synchrony and availability. That means that Alice is online, or Bob for this matter, is able to submit the proof for transaction TX1 being in Bitcoin, and then that this message will be delivered to the smart contract within a known delay. Or we assume a trusted third party that takes over this role and essentially either delivers the message on behalf of Alice or simply replaces the smart contract and enforces correct behavior of Bob. And we need definitely one of these two things to make sure that the protocol is indeed executed correctly and that at no point in time it is possible that either Alice or Bob are left at a disadvantage. Now, from previous research on fair exchange, and also we have this discussion in our paper, we see that synchrony assumptions and a trusted third party are actually to some extent equivalent. And the intuition behind this is as follows. If we assume that Alice is available online and that we have a synchronous communication model, so we know that Alice's messages will always be delivered within a known delay, so we can execute this protocol without having to lock up funds of users indefinitely, then Alice in this case becomes the trusted third party of this protocol. And in this case, it's in her own interest, but there are scenarios, for example, if we use hashtag lock contracts where this is turned around, and then you have to assume that the counterparty is indeed behaving correctly. So when we then design a cross-chain communication protocol from scratch, we need to solve the following problem. We need to decide which trusted third-party model to use at which step of the protocol. And here we basically introduce the cross-chain design framework, where we identify different models for trusted third parties, synchrony assumptions, or hybrid of that at each step, commit, verify, and abort of a CCC protocol. Now, in consideration of time, I won't go into detail here, and again, we'll refer to the paper. But one thing that is very relevant and interesting also in practical perspective is that we generally also identify two main protocol families. Exchange protocols, which basically exchange assets on two different blockchains. And basically what happens is that assets change hands or information changes hands on two blockchains, and this is synchronized. Typically, these protocols implement a two-phase commit protocol and have a dedicated abort step on both systems. Now, another protocol family often encountered it also, for example, in RAP-BTC, also in sharded systems, is asset migration. And the idea here is that you lock up or essentially move asset X from the one blockchain to another blockchain. And here you would typically use concurrency mechanisms. So you obtain a write lock on this asset on the source blockchain. You basically prevent any further state updates to that. You create a representation of this asset of the target blockchain or object, and then you basically execute state updates there. And now when you want to go back, you will propagate these updates back to the source blockchain. And in Wrap Bitcoin, for example, where you move Bitcoin from Bitcoin to Ethereum, you can imagine this as being change of ownership. If I lock my BTC on Bitcoin, move it to Ethereum, and then transfer it to somebody else, and this person decides to redeem the BTC on Bitcoin, ownership has been changed, and then hence the state update is propagated back to BTC. Now we have a very fancy table with all the protocols that refer and design cross-chain communication over the past years. And again, I won't go into details. There's a lot of short abbreviations here, but I do recommend that you take a look at that because it kind of provides a good overview of all existing protocols. Now, today we will focus in the last 2 minutes on XCLAIM, which is basically a protocol that we designed with interoperability in mind, trying to make it trustless, but essentially what we achieve is financially trustless cross-chain communication by using incentives and collateralization. XCLAIM uses the concept and first kind of formalized the concept of cryptocurrency-backed assets. And the idea was that you basically, and I will use Bitcoin and Polkadot in this example, you move Bitcoin from the Bitcoin blockchain to Polkadot by creating a one-to-one representation. And this representation, which we shall refer to as PolkaBTC, can be used in DEXs and stablecoins and any other applications that are available on Polkadot, but are not available on Bitcoin. And then once users decide to go back to Bitcoin, they destroy these assets and receive BTC in return. And essentially this works for any backing blockchain. And there are, however, some requirements for the blockchain where these assets are issued, and I will come to this in a minute. Now, one of the challenges that we tackled with XCLAIM was that we wanted to get this to work for Bitcoin, which means that we have no smart contract functionality, or very limited at least. So what we can achieve is we can lock BTC and mint PolkaBTC atomically because we can build cross-chain light clients on Polkadot and smart contracts capable blockchains. And I'll come to that in a minute. But one of the main challenges on Bitcoin is that we cannot do that here. We do not have any way to verify external events on Bitcoin, which means that we cannot verify the state of another blockchain. So we need to come up with a different mechanism. And the first idea that comes to mind is, well, why don't we use hash term lock contracts? Because this is typically used in mostly all protocols that do something more complex on BTC. Now, the issue here is that by design, Bitcoin UTXOs, when you lock something in a UTXO, you need to know who's going to spend from it. But since we don't know exactly who will be redeeming the Bitcoin after they are transferred on a different blockchain, we do not know this upfront, and hence we cannot create a lock that will be redeemed by a random person in the future. We can also not really store generate secrets in smart contracts. So this leaves us with a problem that we only can either use very, very bad solutions by mirroring all transactions on both blockchains and having it very interactive, or we have to use some form of intermediary. And this also kind of coincides with Impossibility Result. Now, what we do in XCLAIM is we introduce so-called vaults. Vaults are participants that hold BTC on behalf of other users. And the idea is that any user can become a vault, and that vaults lock up collateral to ensure that if they steal users' BTC, they will be slashed and the users will be reimbursed. And we do this by forcing vaults to proactively prove to the issuing blockchain, in this case, the Bitcoin parachain on Polkadot, that they behave correctly using cross-chain SPV proofs. Now, to become a vault, you only need 3 things. You need a Bitcoin wallet, you need a Polkadot wallet to basically receive and make payments, and you need to provide some form of collateral. But what I would like to emphasize here is that while we do have intermediaries, vaults are it's a fully dynamic and permissionless set. So essentially, I can be my own vault if I don't want to trust anybody else for the issue process. And we have smart contracts basically as well, it's not really an intermediary, but it's enforced by the consensus of the target chain. And basically this makes sure that vaults remain or behave correctly or face punishment. Now, if you look at XCLAIM and the architecture that underpins the protocol, it may at first seem that a protocol is very simple, and it is actually, and that's kind of a great thing about it. But if you start implementing it, it does become quite complex because there's a lot of moving parts. You have different modules for different protocols, issue, redeem, and then we also have a protocol where vaults can be replaced by other vaults. We have a module to rebalance collateral in case of exchange fluctuations. So we need exchange rate data from an exchange rate oracle. We have a vault registry to manage all vaults, and finally a treasury to manage the newly minted assets. However, one of the most interesting components is BTC Relay, which is a cross-chain SPV client for Bitcoin. Just like any SPV client on your phone, BTC Relay follows the Bitcoin main chain by downloading and storing block headers, checking the difficulty adjustment, the proof of work, the ancestors of the chain, and then also handling forks in case these occur, and also essentially always self-healing and following the Bitcoin main chain. Now, what we can do if we have this, basically this Bitcoin main state in another blockchain, is we can verify transaction inclusion proofs and cryptographically check that a transaction has indeed been included in Bitcoin. And then we also implement some form of partial transaction validation to be able to check that indeed the transaction looks like it should, so that the payments are indeed made to the correct people. One thing to note here is that we cannot fully validate Bitcoin. So we assume the SPV assumption. And this assumption means that if we follow the main chain, we assume that full nodes will reject invalid transactions. Hence, if a transaction is in the main chain, this transaction has to be valid. Otherwise, it would have been rejected by full nodes. Now, if you look at XCLAIM protocols, we have two main protocols there, issue and redeem. And the issue protocol operates in 3 steps. First, the vault locks up collateral, in our example, the BTC parachain, and we use the Polkadot native currency as example here, so DOT. Now, in the second step, a user will transfer BTC to a vault of their choosing, and this doesn't really matter as long as the vault is able to serve the request based on how much volume the user is actually trying to transact. Now, this actually is implemented as a two-phase commit protocol where the user first requests to reserve the vault's collateral to avoid race conditions, where the vault can try to take out the collateral before the user is able to finalize the request, or multiple users send BTC to the same vault and basically compete for the slot where only one user will actually have the security of collateral. Now, once the user sent BTC to the vault, the user proceeds to submit a proof, an SPV proof, to the BTC parachain. This is then verified, and if correct, the user will receive newly minted PolkaBTC. Now, we do understand that it's typically for normal users, it might be a bit tedious to generate these proofs and submit them. So what we have are another rule in the system, which was not on the slides, namely stake relayers. Relayers are participants just run the software that follows the Bitcoin main chain, submits block headers to the BTC relay to keep it up to date, and then also can automatically submit these proofs on behalf of other users. So similar to the concept of watchtowers. So this can be outsourced for usability purposes, and it's for each user to decide whether they want to do it themselves or are happy to outsource. Now, when the user wants to redeem PolkaBTC for Bitcoin, meaning they want to go back to Bitcoin, the first thing they do is they lock BTC with the BTC parachain, essentially burning the PolkaBTC tokens. The parachain will then emit an event and select a vault or multiple vaults, depending on the volume, which have to serve this request and release BTC to the user. Now, these vaults will transfer Bitcoin to the user and then proceed to submit SPV proofs that indeed they did this as requested by the protocol, and then their collateral will be released. And they can, again, either accept new issue requests or leave the system. Now, of course, if the vault misbehaves, that collateral will be slashed and the user will be reimbursed. In practice, you typically want to make sure that a user can still get the Bitcoin back. So what we have in the background is an auction protocol where users can always get out in BTC, and new users can come in and basically make a very efficient trade between the collateral currency and BTC. However, if you want to do this as a user who has been basically subject to theft, you can choose to execute, slash the vault, liquidate it, take its collateral, and essentially execute a very beneficial exchange between Bitcoin and the collateral currency DOT. So essentially, you're actually financially even better off if you're stolen from. Now, of course, this all depends on the exchange rates. And if these are stable, everything works fine. But as we've seen in the cryptocurrency space, this is often not the case. So we implement a multi-stage collateralization scheme where we assume that we have to over-collateralize vaults to ensure that they are resilient against short-term fluctuations. So vaults don't have an incentive if the price drops significantly to still steal BTC of the user. Now, we assume a factor of 2.0, so we collateralize by 200%. And this is indeed not very efficient, but is in line with what DeFi protocols do nowadays. And then essentially, if we basically go to the next stage, so at a factor of 1.5, between those two factors, everything is fine. And we can assume that vaults will still behave correctly. Now, if the exchange rate keeps dropping and vaults not add more collateral or do not rebalance the system by offering more efficient redeem requests to users against the fee, then what will happen is that we enter the auction phase. In the auction phase, the vault slots are auctioned away to other participants. And this is similar to what we say in MakerDAO's Keeper network, where people can bid collateral to kick vaults out and take over the BTC and take their place in the system and earn fees on their behalf. Now, alternatively, a vault can offer users to redeem. In this case, the vault can be forced to redeem BTC to users, but also pay them a fee for doing so. That means we incentivize users to get BTC out of the system to rebalance the mechanism. But if nothing else works, we enter the liquidation phase, where essentially vaults are instructed to release Bitcoin back to users. if they do not do so, they are slashed. And in this case, we're still at a rate where vaults financially are not incentivized to misbehave, and we can get all the BTC back to the users without them facing financial damage. Now, of course, this can be an opt-in, opt-out mechanism depending on how the users prefer to execute the system. But essentially, what we hence guarantee is either a user can get their BTC back, or they'll make a very beneficial exchange for the collateral currency, which is financially trustless in that sense, because you don't face financial damage. Now, looking at the system requirements on the backing blockchain, and this was one of our main goals, we have no additional requirements at all. You only need to be able to make Bitcoin payments or essentially transact different cryptocurrencies. On the issuing blockchain, where we need some form of smart contracts or some advanced functionality, we need a chain relay component. So we need to verify the state of the backing blockchain. We also then need to support some form of on-chain assets to be able to mint these tokens and to have conditional payments to handle collateral. So essentially, any blockchain that supports smart contracts can be the issuing blockchain, but we support all blockchains without restrictions on the backing side. Now, we do know that if we have smart contracts on both sides, this does make things a bit more secure because we can run chain relays on both blockchains and just verify the state of each other, basically making sure that we no longer need vaults or collateral. In this case, vaults can be employed as an optimization for performance and cost because synchronizing two chains cross-chain and tracking each two different blockchains does indeed incur an overhead and some complexity. That's basically what we've done so far. We're currently working to make sure that vaults actually cannot steal user funds at all. And this way we can significantly reduce collateral. In fact, we have this in draft form. This will be released within the next 1 month or so. And this is basically an extension to the current protocol, which makes it very interesting for DeFi applications. We've also been working on avoiding clock synchronization across different blockchains using relative time locks, and also working on making sure we can lock collateral directly on the backing side, so in Bitcoin, which would completely avoid collateralization. So thanks a lot for the attention and happy to take any questions.
Thank you, Alexei. So you can write questions in the chat or raise your hand. There is already one question from Isaac, who asks, do users have to trust that the Bitcoin parachain will not work? Like, how is the parachain run exactly?
So, I mean, the parachain is beneath Polkadot's consensus, essentially. So in any case, when you transact between two blockchains, you need to assume that both blockchains have persistence and liveness. Of course, if Bitcoin breaks or the parachain breaks down completely and is subverted by an adversary, this protocol will break. But that's a general assumption that you have to make when you transact between two systems. You have to think of it this way. Why would you move Bitcoin to another blockchain if you don't think that it will indeed be secure there?
Can you elaborate a bit on what you said on Synchrony's equivalent to trust third party, especially when you said about time lock contracts and how you have to trust the other side? I didn't totally get that.
So, I mean, the time lock contract was an example for actually HTLC atomic swaps, because often when we present this result to the Bitcoin community or developers in the space, HTLCs are often brought as an example that they are trustless. But essentially, you have to assume that one of the parties or both of them are online and basically make actions according to the protocol specification. Otherwise, you are maybe subject to theft. In an atomic swap using HTLCs, for example, what can happen is that if one of the parties goes offline, but has already made the payment and fails to reclaim the funds from the counterparty by spending from the output of the other blockchain using the secret that was revealed, then when the time lock expires, the counterparty can then take back its own funds, but has already received the payment, and there's no way to revert that payment. So you basically, because you were not online, you faced a failure. So in this case, Alice, who was in a previous example, the party that would have to submit the proof or claim the payment cross-chain, becomes its own trusted third party. Alice either assumes that she can do it herself and that she will be online and that her messages, so the message that she sends to spend from the other output, will be delivered on time, or she has to employ a trusted third party to do this.
Okay, so you only trust your ability to reach the message on time.
Exactly. So there's kind of two assumptions, which essentially in practice are the same, but either you have a Synchrony availability assumption that you will be able to do it yourself, or you have to employ a trusted third party. In practice, of course, we can work around these, and this is a theoretical result, and hence we still have atomic swaps that work in practice and XCLAIM. But essentially, if it all if push comes to shove, you always burn down to either you're online and your message will be delivered, or you have to employ a trusted third party.
Okay, so Dunkard is asking, what's the advantage of this, I assume XCLAIM, over having a CDP-only design, basically Maker, but for Bitcoin?
That's a very good question. And in fact, XCLAIM currently is a hybrid. So it's backed by collateral, but this collateral is there to ensure that vaults do not steal. You do have physical Bitcoin locked up, which ensures that you don't have inflation of supply. If you only have collateral-backed assets and you start transacting cross-chain, it may end up looking like you have more BTC issued than there actually is. This may have more macroeconomic impact. In the short term, may not be a big problem. However, this becomes really interesting if you actually want to trade the underlying assets. It's like essentially when you buy gold, you'll never be able to actually get your gold out of the bank typically, but you still assume it's there. And if you were to basically print gold based on the USD locked in the bank, that would kind of break its assumption and kind of the value, that proposition that's behind it. In the new system that we're currently designing and we have in draft form, in fact, we get rid of the collateral requirements for 99% of the time, and it becomes a physical peg essentially, where you don't need collateral. And in that case, you just physically move BTC between different blockchains, and you can rely on the scarcity of the actual asset that's backing this newly minted assets.